So as we start these examples of the fundamental theorem of calculus part 2, or just evaluating that definite integral, we're going to start with example 1, where we evaluate the integral of x cubed dx on the interval from -2 to 1. So using that fundamental theorem of calculus, we understand that we're looking for that antiderivative of our upper limit minus the antiderivative of our lower limit. So if I find the antiderivative of this function, f of x is simply running that power rule plus c. Now, in the video that you watched previous to this, they never really addressed what happens to that family of functions with the plus c. Well, when we plug our f of 1 in and we plug our f of -2 in, you're going to see that it actually is going to cancel out. So we lose that general antiderivative, or we lose whatever constant we may have had. So in evaluating this function, f of 1, we're going to get a value of 1/4 plus c minus, then we're going to evaluate -2 plugged into the function. So that's going to give me -2 to the 4th power over 4 plus c again. So you can see when I distribute that negative that these two c's are essentially going to disappear. So that constant, when I evaluate a definite integral, will not matter anymore. In an indefinite integral, that c could matter. All right, so we're going to finish evaluating this, and we're going to take 1/4 minus, if I take -2 to the 4th power, that's going to leave me with 16, and 16 divided by 4 is 4. So I end up with a value of 1/4 minus 4, or simply -3 3/4. Okay, looking at our example 2, it says find the area under the curve of y is equal to x squared from 0 to 1. Now previous to this, we would be using a Riemann sum to do this, but we found that fundamental theorem of calculus part 2 tells us that it takes the Riemann sums and it puts an infinite number of rectangles in there for us. So in this case, we're just evaluating the integral from 0 to 1 of the function x squared dx. So again, I'm going to calculate what that f of x function looks like. And that f of x function looks like x cubed plus 3 divided by 3 plus c. So that gives me the function f of 1 minus f of 0. So plugging that into the function, I get 1 cubed minus 0 over 3, or 1 over 3, which is 1/3. And this would be square units, since it's talking about area in this problem. All right, for our third problem, you see it adds in a trig function. So what I did over here was I just kind of put those trig, our important triangles in here, our 45, 45, 90 triangle and our 30, 60, 90 triangle, to get us to remember those exact values for our 30s, our 45s, and our 60s. All right, so we're asked to find the integral of sine of t dt. Well, I have to know what the antiderivative of sine is, so the antiderivative is going to be negative cosine of t. But now I'm going to evaluate this from pi over 4 to pi over 3. So I found my antiderivative. I know that that plus c is not going to matter in my definite integral, so I went ahead and omitted it. So now I'm going to evaluate this as negative cos of my upper limit minus negative cosine of my lower limit. So using those triangles, or you can use a calculator or even the curves of the function, I look at the cosine of pi over 3. So the cosine of pi over 3 is 1/2. So my first value is going to give me a negative 1/2 minus, and now I'm looking for cos of pi over 4. Well, cos over pi over 4 would be 1 over the square root of 2, or when rationalized will give me the square root of 2 over 2. And since it's negative, this is going to result in the negative square root of 2 over 2. Fix my double negative, and I end up with the square root of 2 minus 1 divided by 2. That's our exact value for the integral of sine of t. For my fourth example, you're going to notice that this is a piecewise function. So we're integrating the function f of x, where the f of x is broken into pieces. So I'm going to use one of the properties of integrals that says that, okay, I can break my interval into pieces. So I can see that I've got to integrate for my interval 0 to 1. I'm going to integrate the function x to the 4th power. And then from 1 to 2, I'm going to integrate the function x to the 5th power. So you're going to see that I'm going to just take and rewrite this function in 2 separate pieces. Okay, so now I calculate my antiderivatives for the first piece, x to the 5th over 5, and we're going to evaluate that piece from 0 to 1. In addition to that, I'm going to integrate x to the 5th as x to the 6th over 6, and we're going to evaluate that from 1 to 2. So what I get for my first piece is I get 1/5 minus 0, and then I'm going to add that on to 2 to the 6th power over 6 minus 1 to the 6th power. I'm going to pull this up because we're running out of room over here. So I'm going to end up with 1/5 plus 2 to the 6th is going to give me 64 over 6 minus 1/6 gives me 1/5 plus 63rd over 6. And when I simplify that out, quick calculation here, 1 divided by 5 plus 63 over 6 gives me 10.7 for my integral.